Every day, you open a map app on your phone, type in a destination, and hit the navigate button. In less than a second, a highly optimized route appears on your screen. It feels like a simple lookup request. But the North American road network alone is a sprawling web of more than 64 million distinct intersections. Using basic route estimation, paths from point A to point B rapidly branch out to an astronomical 10 to the 220th power. That is a physical wall. Even calculating 100 million routes every second, a supercomputer wouldn't finish before the universe ends. Today, in a live business environment, tech companies are serving millions of impatient drivers at the same time. If a navigation server took even 7 seconds to process a single user's route, the sudden spike of rush-hour traffic requests would instantly crash infrastructure worldwide. Hitting a sub-millisecond response time is mathematically impossible to achieve with raw hardware power. Solving the pathfinding problem required a structural trick invented decades before the modern internet. The foundation of modern navigation was laid in Amsterdam in 1956. While having coffee with his fiancée, a programmer named Edsger W. Dijkstra conceived the core logic for calculating the shortest path between two cities. He did the math entirely in his head over the course of 20 minutes without using a pen or paper. The logic of Dijkstra's algorithm is brilliantly simple. It expands outward from a starting point in all directions, like a ripple in a pond. As the ripple touches each adjacent intersection, or node, it logs the shortest known distance to get there, creeping forward until it finally hits the destination. The algorithm guarantees you will find the absolute shortest path. But for a modern application, it is far too slow. Searching street by street across a continental map using this method takes an average of 7 seconds per query. Engineers tried to patch the speed issue with A-star search. This added a directional compass to the math, actively punishing the algorithm with higher mathematical costs if it tried to calculate routes heading in the opposite direction of the destination. A-star search works perfectly for physical distance, that it fails in real-world commuting. Drivers care about travel time. A-star lacks the intuition to realize that a long, looping interstate is much faster than driving in a straight line down a gravel road full of stoplights. Next came bidirectional search, starting a ripple at the origin and the destination simultaneously until they meet in the middle. This halved the search area, but it still treated a dirt path and an 8-lane highway as equal options. The machine still lacked a human driver's intuition for road hierarchy. Step-by-step optimization had reached its limit. To get response times under a millisecond, engineers had to stop treating every road equally and completely reinvent how computers perceive map data. The ultimate solution is a ruthless data filtration system called Customizable Contraction Hierarchies, or CCH. In Phase 1, the system pre-processes the entire map using nested dissection, a mathematical method of slicing regions in half over and over to identify massive, unavoidable geographical choke points. This phase automatically builds a digital road pyramid. Dead-end streets and local dirt roads are assigned the lowest priority at the wide base. Transcontinental bridges, tunnels, and interstates are extracted and pushed to the very top. To prevent the system from aggressively routing a driver onto the highway just to visit a grocery store 1 block away, the algorithm tests the bottom layer. Where local trips are genuinely faster, it injects artificial shortcuts directly into the database to bridge them. In Phase 2, the system handles live traffic variables like rush hour jams or accidents. Instead of redrawing the entire map, the servers simply update the specific travel time numbers attached to the affected roads. The heavy pyramid structure remains perfectly intact. Phase 3 is the live query. When you ask for a route, the system executes a bidirectional search with one unbending rule. It is forced to only search up the pyramid. Once the search reaches a highway tier, it completely ignores the millions of local roads sitting beneath it. The metrics drop instantly. A coast-to-coast calculation time plummets from 7 seconds down to 200 microseconds. Out of 64 million possible intersections, the algorithm only has to check about 1,200 of them. CCH achieves its blistering speed through strict omission. It guarantees a flawless route, not by searching the map faster, but by intentionally deleting 99.9% of the map from its active memory before the search even begins. This microsecond pathfinding architecture dictates the physical movement of the modern world. It is the hidden engine calculating ride-sharing ETAs, batching food delivery orders, and charting the cheapest routes for global freight logistics. Modern technology companies often default to throwing massive server farms and raw processing power at complex problems, but the infrastructure of digital navigation proves the superiority of algorithmic elegance. While computing hardware has advanced by orders of magnitude since the 1950s, pure processing power is rarely the answer. The way a machine logically structures its data remains the true bottleneck. When Dijkstra designed his initial algorithm, the lack of paper forced him to keep the logic completely streamlined. He later noted that avoiding unnecessary complexity is the strict prerequisite for building reliable systems, the only way to handle millions of simultaneous users without collapsing. The entire multi-billion-dollar digital logistics economy manages to run smoothly every single day, and it rests entirely on the mathematical restraint born in a 20-minute pen-free brainstorming session 70 years ago.